Dear students, good evening to you all. I am here to present a lecture on Proton NMR Spectroscopy. You may get questions. What is Proton NMR Spectroscopy? How we have to learn this Proton NMR Spectroscopy and where it is used in our daily life activities. Let us see. Dear students, look at the slide. The Proton NMR is meant for only structural determination, and this Proton NMR technique is used in magnetic resonance imaging, which is popularly called as MRI scan. And Proton NMR is also used in quality checking in food material, structural biology, and widely used in drug discovery process. You see, dear students, from small laboratory to the worldwide research centers, the researchers are struggling a lot to get a vaccine or a drug for COVID-19. And you see, the synthesis of drug discovery is not a simple process, and it involves so many prolonged steps. And if you see the fundamental criteria of drug discovery, it involves the designing of the drug with respect to the target molecule, and that drug should be synthesized in the laboratory. After that, we have to go for biological evaluation. Biological evaluation in the sense, evaluation of anti-COVID property, evaluation of anti-cancer property if we are working for a cancer drug, evaluation of antimicrobial property, antibacterial, and so on. If you look at the synthesis part, let me take one example. Let us assume that we have designed a drug D from starting material A in some steps. Those are conversion of A to B in the first step, and in the second step B to C, and in the third step C to D, which is a drug molecule here. I have given you this starting material and all the required reagents, and I asked you to perform the reaction in the laboratory. And after completing the reaction, you get something, but we are not sure that is B only or something else. If it is B only, it can be determined by structural determination methods. If it is B only, then we can go forward. If it is not B, we have to come back, we have to change the starting material or the path followed for the conversion of A to B. Like that, in each and every step, the product should be structurally confirmed. Then only we have to go further. Okay, this is only example. If you take Taxol, which is a drug used for cancer, it involves 19 steps for its synthesis. If you take some other drugs are also, which involves 50 to 70 steps are also for their synthesis. From this, you can come to a conclusion that, dear students, the synthesis of drug involves synthesis of plenty of organic molecules which should be structurally determined. How can we do structural determination then? Let us go back to 1940s. The methods available at that time were very conventional. Those include decomposition into fragments, elemental analysis, and mass spectroscopy. If you take the first method, it involves fragmentation of the complex molecule into small molecules, and those small molecules were compared with already known molecules, thereby they can predict the structure of the complex molecule. If you take elemental analysis, by this method we can only determine the type of atoms and the composition of atoms present in that particular molecule. And if you take mass spectroscopy, it gives the information of molecular weight of the compound. Let me check out whether these methods are succeeded in determining synthesis, structural determination of organic molecules. On the screen, you are able to see 3 molecules. If you observe, each molecule contains same carbons and same hydrogens, 5 carbons and 12 hydrogens. If you count the molecular weight, if you calculate the molecular weight, C5H12, 5 into each carbon 12, that is 60, and 12 into each hydrogen molecular weight is 1, that is 60 plus 12, 72. By that we can determine the molecular weight, and the same data is given for these 3 molecules, and we could not find whether the molecule particularly we got, and hence at that time a updated method is needed, and that problem had overcome by the discovery of NMR technique by Isidore Rabi in 1938, for which he awarded Nobel Prize in 1944. You see, dear students, starting from 1944 till date, this branch of spectroscopy brought 5 Nobel Prizes. Do you know that, dear students? Okay, let me introduce the topic nuclear magnetic resonance spectroscopy. Let us examine the meaning of each word in it. First word is nucleus. Look at the screen, dear students. Nucleus means the central part of the atom, which consists of protons and neutrons around which electrons are revolving. And one more thing we know about nucleus is the protons are positively charged and the neutrons are not having any charge. And next word, magnet. From our childhood we all know that the substance which exhibits the property of magnetism is magnet, and it have north pole and south pole, and the magnetic forces of lines flows from north pole to south pole. And one more thing we know about this magnet is, in the presence of another magnet, this magnet can be reoriented depending upon the orientation of poles, that is north and north poles repel each other, north and south poles attract each other. We know very well. And next word, resonance. Resonance, it is the physical phenomenon. If a system is under the influence of external source, and if the frequency of external source and the frequency of system matches with each other, the system takes maximum displacement. This can be explained easily by resonance phenomenon in swing. If you take swing, the swing has its own natural frequency, and the throwing person exerts some force which has its natural frequency. If these two frequencies coincides or matches with each other, the swing moves maximum displacement from the central position. This is about resonance. Next word is spectroscopy. As science students, we all know that spectroscopy, the study of interaction of electromagnetic radiation with matter, is spectroscopy, and in NMR technique, radio waves are allowed to fall on nucleus to produce the spectra, because the electromagnetic spectrum is a combination of so many frequencies ranges, right, like microwaves, ultraviolet, visible, infrared, like that. NMR requires, or the most suitable frequency of NMR is radio frequency. Let us correlate these now. When radio frequency is allowed to fall on nuclear magnets, resonance phenomenon occur, thereby producing a peak in NMR spectra. And here I am using the word nuclear magnet. What do you mean by that? My question is, do all the nuclei act as magnets? The answer is definitely no. Let us see how it is. Here, a molecule, in order to show the magnetic property, the nuclei should possess particular number of protons and neutrons. See that in the table I have given different types of protons and neutrons, and the combinations of even and odd number of protons and neutrons. In the first case you see even combination, and here what happens means adjacent spins cancels each other, producing 0 quantum number, that is 0 spins. Why? Because they cancelled each other. There is no resultant spin at all. No resultant spin means no magnetic moment, that is no magnetic property, which is NMR inactive. If we take case 2, I have given odd even combination. In odd number we get one unpaired proton here. Because of that one unpaired proton, we get resultant spin. Here proton is spinning, right? Proton is spinning means charge in motion. From our elementary physics we know which a particle or charged particle, if it is in motion, it produces electric field and magnetic field perpendicular to it, and hence this particular nucleus acts as a proton, and hydrogen proton is the best example for this. And the spin states, if you take spin, half will be there, and spin states 2 into 1 by 2 plus 1 is 2. And if you take case 3, even odd combination, here you may get a doubt, because here the unpaired particle is neutron, which is not at all having a charge. But initially I was telling that the charged particle only produces magnetic field. Here, even though neutron is not having any charge, it have positive and negative charges within it, that is, it is a dipole, and because of the movement of the dipole we get a new resultant spin, thereby it is NMR active, that is, it produces magnetic field around it. If we take case 4, odd combination is there, in that both are existing, odd number of unpaired proton and unpaired neutron, by which we get integral spin. Here I have given the notation here x, and in this place I have given number of protons, here number of protons plus neutrons. Why I have given this means, in PG entrances like that you may face question like this: which of the following molecules are following nuclei or NMR active? In that case, just remember that you should find an odd number, whether in this position or in this position. If you find odd number, then it is NMR active. Let us see some examples. Here, first nucleus is proton. See, it is having odd number of protons, active. Hydrogen nucleus, active. Helium, it is not active. Why? Because even combination. And nitrogen, active. And magnesium, not active because of even combination. And phosphorus, active. Like that, a nuclei must possess with odd number of protons or odd number of neutrons or both odd number of neutrons in order to exhibit the NMR phenomenon, that is nuclear magnetic resonance phenomenon. Because of this only there exists precessional motion for the nuclei, because of this spin only. Let me introduce the word precessional motion of nucleus. Look at the screen, students. Have you seen this one ever? That is spinning top, that is we say bongaram, right? You may played with it while you were a child. Just imagine that this spinning top is revolving in front of you. If you keenly observe the motion of the spinning top, you can find two types of movements. One is the spinning top around its own axis, and the other is it is spinning around the axis of the earth, that is a valve like motion is also observed in the spinning top. Okay, why I am telling this means similar type of motion we will observe in case of nucleus also when it is kept in the external magnetic field. See here, that is the precessional motion of nucleus around itself as well as around the direction of the magnetic field. Like that, there exists precessional motion in nuclei. And look at the screen, students. Here on the left side, you can observe the spinning or precessional motion of spinning top around the gravitational axis, and on the right side you can observe the precessional motion of the nucleus around the axis of external magnetic field. Why I am telling this precessional motion means because of the precessional motion only there exists precessional frequency for that particular nucleus, and because of that precessional frequency, it should be matched with the frequency of radio waves, thereby producing a peak. Let us see the principle of NMR. Dear students, let me ask you one question before principle of NMR. What is the molecular formula of water? You all know, that is H2O. have you ever think that how many water molecules are there in a raindrop? Have you ever think that? Let me tell you, the number is 1.6 into 10 to the power of 21. That is, after 16 we have to keep 20 zeros. See, such a big number that is. And have you ever think how many sucrose molecules are there in a sugar crystal, small sugar crystal from the sugar bottle at your kitchen? Let me tell you that also. The number is 7.3 into 10 to the power of 21. See, this is also such a big number. That is, a pinch of molecule, a pinch of compound also exists with so many number of molecules. In NMR technique also, the technician usually takes 3 to 5 milligrams of the compound. That means a pinch of compound. We can imagine that pinch of compound as millions of molecules, and which in turn contains atoms, which in turn contain nucleus, right? So we can imagine the pinch of the analyte what we are taking to record NMR spectrum as a sea of nuclei, and all the nuclei are oriented randomly in different directions before keeping it in NMR machine. But when we keep that in NMR machine, that is in between the magnetic poles, because of the presence of external magnetic field, it aligns in two directions. One is along with the magnetic field and another is opposite to the field. Look at the screen, students. If you observe, this is the direction of external magnetic field, and these are the spins oriented along with the field, which are in pink color, and these are opposite to the field. Those nuclei which are present along the field are said to be in alpha state, and those which are opposite to the external field are said to be beta state. Now let us know more about this. Look at the screen, students. Here, if you observe the sphere, blue colored sphere, what is that? That is nucleus. And if you observe the direction of that nucleus, it is along with the direction of the magnetic field. Look at there, the direction of the magnetic field, which I represented as in green arrow. So these two are same direction, and hence the nucleus is said to be in alpha state. Okay, what it is doing there, what the nucleus is doing there, it is not simply sitting, it is precessing in the presence of external magnetic field. Okay, good, no doubt about it. In this situation, when we allow radio waves of variable frequency upon the nucleus, what happens? You know that resonance takes place. When the frequency of radio waves matches with the frequency of nucleus, resonance takes place. Resonance takes place means absorption of energy, thereby flipping of the spin, going to beta state. So it came to beta state now. The alpha state nucleus turned into beta state. Let me tell you another thing here. This beta state, the nucleus in beta state, it is not stable there. It is not happy there, and it want back to alpha state by releasing same amount of energy which it was observed earlier. And that signal will be detected by the detector, producing a peak in NMR spectrum. Like that, we get peak in the NMR spectrum. If you observe the equation, the nucleus in alpha state turns to beta state by absorbing energy and back to alpha state by releasing same amount of energy, producing a signal. Here the energy absorbed by the nucleus which is in alpha state is given by delta E equal to h nu. H is Planck's quantum number and mu is precessional frequency. Here you know one thing here, students, the precessional frequency of this nucleus depends upon the external field. Let me tell you one example here. You might be seeing at your homes the regulator of ceiling fan which is attached to switchboard. If you observe that, if we adjust the regulator to first stage, what will be the speed of the fan? And if you increase the speed by gradually by 2 to 3, 3 to 4, 4 to 5, If it is adjusted to fifth stage of the regulator, the speed of the fan is more compared to first stage of the regulator. Like that, here also in the presence of magnetic field it precesses, okay, but if the strength of the magnetic field is low, its precessional frequency is also low, that is it precesses with low speed. And if the strength of magnetic field is high and its precessional speed, that is precessional frequency, is also high. Remember that the precessional frequency depends upon the strength of the external magnetic field, and which is equal to the frequency of the radio waves. Here delta E depends upon the strength of the magnetic field also. See, if you look at the screen, that image, till now we talked only theory, right? This is the image of the proton NMR machine. It actually looks like this, and the spectrum we can observe on the computer screen, which is connected to proton NMR spectrum. And in this image you can observe the new NMR tubes in which we take sample solution to record the spectrum. And we take the sample in NMR tubes, and we keep that NMR tubes in between the poles of the magnet, thereby, and here from RF transmitter, RF radio frequencies will, or radio waves will be generated, irradiating the samples, and the resonance takes place here itself, producing a peak, producing energy which is in the form of radiation, and that radiation will be absorbed by the detector, producing a peak in NMR spectrum. See, NMR spectrum is a graph. On x-axis we will take frequency as a function of field strength B0, and on y-axis we take absorption value. Here I have shown only one peak, right? But if a molecule have 10 types of nucleus, we should get 10 peaks in the NMR spectrum, and this depends upon 10 peaks in the spectrum. Depending upon the electronic environment. Okay, getting up of peaks is not enough. It is not that much informative, because with reference to a standard only we have to study the peaks. Why? Because let me tell you one example, students. You might be seeing in sports competitions like running race, that one, what we say, javelin throw. Have you seen javelin throw and shot put? In such type of games, what they will do? They will start from a reference point, and by measuring the distance covered by the players from that reference point only, and they says that certain player has covered this much distance and another player has covered this much distance from the reference point only. Without that reference point, the competition is meaningless, right? Similarly, here also a reference should be there in order to study the peaks of the compound in NMR spectrum. And after prolonged research, the researchers has found that a chemical called tetramethylsilane, which is more suitable for standard in NMR spectrum, which is called as internal standard. Look at the structure, students. Here the methyl groups, 4 methyl groups are attached to silicon, and the 4 groups are same, and hence 12 protons gives same signal, singlet, in proton NMR spectrum. And if we compare the position of the peaks, we get all other organic nuclei gives at a higher frequency compared to tetramethylsilane frequency. And the other reasons for taking this as internal standard, because it is chemically inert, it won't react with the compound what we are taking, and it is highly volatile also. See, in the figure I have shown the NMR tube. If you see, after analysis, if you remove the green colored lid, the tetramethylsilane will evaporate within half an hour or 1 hour, producing our compound back. See, for the researchers, getting the compound back is very useful sometimes, and hence by using tetramethylsilane as internal standard, we study the position of peaks in the NMR spectrum. And that position is studied by a scale called chemical shift, and chemical shift is the resonance frequency of the nucleus relative to the standard in a magnetic field. That is the distance from the TMS peak, that's it. There is no harder thing in it. And if you want to measure in the mathematical form of chemical shift is given by shift from TMS by operating frequency taken in hertz, and the chemical shift is measured in units of ppm, parts per million. And the chemical shift we can study in two scales, alpha scale and tau scale. In delta scale and tau scale. In delta scale the TMS is calibrated to 0. Look at the slide, students. And in tau scale the TMS is calibrated to 10, and the space which is the frequency range which is nearer to TMS scale is said to be upfield, and the space which is farther from the frequency range farther from the TMS scale is said to be downfield. Let us assume we got two peaks in NMR spectrum on delta scale. A peak was observed at 2 and another peak at 9. Then we say that the peak at 2 is called as upfield protons. Because of upfield protons only, upfield region only, we got peak at 2, and if we take the peak at 9, it is said to be in the downfielded region. And this is the NMR spectrum of acetone. On the screen you find the structure of a molecule. This is called as acetone. In our real life it is used as a nail polish remover. You might all seen this. And if you observe the structure, we have 6 protons which are equivalent and give same signal in NMR spectrum. And if we measure the distance in ppm, parts per million, we got 2.14 delta ppm, which is the chemical shift value of acetone. And this chemical shift value depends upon the electronic environment and electronegativity of neighboring atoms. Let me show the chemical shift value of some molecules here. If we take alkyl protons, the chemical shift on delta scale. If we take alkyl protons, the chemical shift is observed at 0.9 delta ppm. If we take alkynyl protons, the value will be from 4.4 to 6, and in acetylene or triple bonded carbon we got the peaks at 2 to 3. And the alcohol peak, the proton of alcohol group we observe in between 1 to 5, and if we take phenolic group, phenolic hydrogen, we will get the peak from 4 to 10, and if we take aldehyde group, we will observe the peak at 9 to 10, and COOH, that is carboxylic acid, 10 to 12, like that. Like that we will get the peaks in NMR spectrum depending upon the electronic environment of that particular molecule. Now let us see what is shielding effect and de-shielding effect. Before that, you should know what is induced magnetic field. Till now I talked only about nuclei, right? But around the nuclei, electrons are also there, no? So because of the electrons around the nuclei, they also produces magnetic field when it is present in the external magnetic field, and that magnetic field is called as induced magnetic field. And that induced magnetic field, sometimes it will be orient with the or in the same direction with the external magnetic field, or sometimes it will opposes the external magnetic field, that is opposite to the external magnetic field. That is said to be shielding. If it is in the same direction, we call it as reinforcing of the field, that is de-shielding effect. Let us see what is shielding and de-shielding in detail. Look at the slide, students. Here I have shown the magnetic field, and this is the red colored arrows or the direction of magnetic field, and the white arrow is the spin. See, it is in the same direction, right? If the spin of nuclei is in the same direction, what we call the state as alpha state. So it is present in alpha state. in order to get a peak in NMR, what should we do? We have to irradiate this with radio frequency, right? Okay, by absorbing the energy from radio frequency, resonance takes place and it goes to beta state, thereby producing a peak. Okay, up to this very nice, but electrons are also there around the nucleus, right? If the magnetic field exerted by these electrons are opposite to the external magnetic field, the spin of the nuclei completely not reinforced with the field, there exists some opposite direction, right? Let me tell you in detail. Let us consider this field as 30 units, and in case of A, the white arrow, that is nucleus, experiences 30 units of the magnetic field, but here it was opposed by the 30 units of magnetic field is opposed by some induced magnetic field. Let the induced magnetic field is 4 units. Okay, here 30 minus 4, 26 only it experiences, the 26 units only here experiences. Here high field strength, here low field strength. Then where will be high precessional frequency there? Here it will be high precessional frequency. High precessional frequency means high energy is required. But here if you look at the arrow, it is with small efforts only we will bring it back to beta state, and hence low energy is needed for this, and hence if the electron density is high around the nucleus, easily with minimum energy only they will come to beta state, and with minimum frequency only they will resonance takes place. Whereas in case of low energy, low density of electrons, there is no induced magnetic field, thereby we have to give high amount of energy to get back to beta state. One thing you should remember, that's it. If high electron density is there, low precessional frequency. Low electron density is there, high precessional frequency. That's it. In this case, high energy is here and low energy is here. In case of B, low energy, and in case of A, high energy. Here, look here. In case of B, E2 I labeled just. In case of A, E1. So, we get the peak at E2 which is nearer to TMS, that is at lower frequency ranges only. So, the B peak is said to be at a low chemical shift and A peak is said to be high chemical shift on delta scale. Okay. And by this example, you will able to clearly understand what is shielding and deshielding. See here, I have taken the example of ethanol, and in ethanol we have 3 types of protons. Here this carbon contains 3 protons and this carbon contains 2 protons, and the hydroxyl group contains 1 hydrogen. Okay, up to here it is very clear. What is there something else? Because of presence of oxygen, it attracts the electron pair towards itself, right? So, here it takes up the electrons from the adjacent atoms. So, the electron density around this hydrogen will move to oxygen in polar solvents, whereas here also somewhat not that much here somewhat there will be effect of oxygen and the electron density will be diminished in this case. And if you look at here, these 3 protons are leastly affected, and hence the electron density of these protons was not taken by anyone, and these have high electron density. What I told you already, high electron density is nothing but low frequency, and hence we observed the peak at low frequency only, that is nearer to the TMS signal, and this is said to be upfield. Already I told you this one. And this OH protons which is having least electron density will be shifted to deshielded region, and it is said to be downfield. In PG entrance exam like that, you may get questions in ethanol which are shielded protons and which set of protons are deshielded, like that they may ask you. And here shielded protons means upfielded peak, the deshielded means downfield peak. And you just remember that Upfield means shielded, downfield de-shielded. You remember the word drawing DD in US bank. Just you remember, it will be useful for you in your competitive exams. By that shielding and de-shielding only, we get equivalent and non-equivalent protons, right? What do you mean by equivalent and non-equivalent protons? If the protons present in same chemical environment, those protons are said to be chemically equivalent protons or chemical shift equivalent protons. Look at the screen, you can find the examples here. See, the first molecule is methane. On the screen it is looking like a plus shape, no, but in reality the three-dimensional picture is this one. The three-dimensional picture is this one. See, carbon and 4 atoms are equally present, equally oriented in space, and the 4 protons are said to be similar. See the second molecule on the screen. See the second molecule, the methane, one of the hydrogen is replaced by bromine. Here the carbon is attached to 3 hydrogen and 1 bromine, and here also these 3 are oriented at a same distance from this green color, which is bromine, and these also said to be chemically equivalent protons. And if you look at the structure benzene, the 6 protons are chemically equivalent. Non-equivalent protons, those protons which are present in different chemical environment, those are said to be non-equivalent protons or chemically non-equivalent protons or chemical shift non-equivalent protons. You see, ethyl bromide, I have given the example. On first carbon, the yellow colored protons are chemically equivalent, and hence these 3 gives same signal in NMR spectrum. And here the 2 hydrogens which are in red color, same signal, that is the ethyl bromide gives 2 signals, and these 3 protons and these 2 protons are said to be chemically non-equivalent protons. And if you take ethyl, let me show you. This one, this is the black balls are 2 carbons, and the white these white balls are hydrogens. If you see the orientation of hydrogens, all are same, 4 hydrogens are same. If in this situation, if we remove one of the hydrogen and if we keep chlorine atom, let us assume that this carbon, this green color ball is chlorine atom. See here, this green ball is nearer to this one, which is said to be in cis position, and this hydrogen is far away from the green ball, said to be trans position. That's why even though the 2 hydrogens are present on the same carbon atom, these 2 are not equivalent protons. Look at the screen, you can find the structure of ethylene chloride. The 2 hydrogens are not equivalent. Why? Because this yellow colored hydrogen is cis to chlorine, this is trans to chlorine. That's why in this particular molecule we get 3 signals in NMR spectrum. You see here, these are the isomers of pentane. In N-pentane you can find 3 types of protons. Here the protons on this carbon and the last carbon are same. Similarly, the blue colored protons are same, and the CH2 protons are different. Like that we get 3 signals in NMR spectrum. If you take isopentane, here 4 signals we will got. Look at the structure, you will find the difference between different hydrogen atoms which are present in different chemical environments. And if you take neopentane, the 4 methyl groups are same, producing a single signal, and these are chemically equivalent protons. Let me tell you one example, other example here. What is this, students? Benzene. How many hydrogens are there? 6 hydrogens are there, right? The 6 hydrogens are chemically equivalent, those are same, and hence gives a single peak in NMR spectrum. Let us assume one of the hydrogen is replaced by methyl group CH3 and these are as usual, no? Hydrogen, hydrogen, hydrogen. See, because of the presence of methyl group, the environment of these 5 protons has changed. Look at the structure carefully. These 2 protons are same, giving a signal in NMR, and these 2 protons are same and this is same because of ortho, meta and para positions. So, mono substituted benzenes gives 3 signals in aromatic spectrum. Like that, non-equivalent and equivalent protons can be explained, and because of equivalent and non-equivalent protons only, spin-spin coupling occurs in NMR spectrum. Let us see how it will be. Look at the screen, students. If you see the first compound, it is having, just a hypothetical case I have taken, it is having no hydrogens on surrounding the adjacent carbon. The yellow colored hydrogen, it is not having any adjacent hydrogens. In this situation, when we keep this type of particular molecule in NMR machine, what will be the magnetic field experienced by this yellow colored proton? That is B naught only. Only one magnetic field strength it will be observed, and depending upon the precessional frequency, it will give a peak. Okay, no problem here. If you take one adjacent proton which is shown in blue color here, this yellow colored hydrogen is adjacent to this hydrogen, and this hydrogen, because of the electrons surrounding this nucleus, there exists induced magnetic field, right? Because of the induced magnetic field, this field strength may vary. Let me tell you why. Let us assume this B naught field strength is 30 units. Okay, and the induced magnetic field of blue colored one is 1 unit. Here 30, here 1. The 1 unit of magnetic field strength may be along with the external field strength or opposing to the field strength. Here I am telling that 30 units, and here if it is parallel or reinforcing, it will be strengthened by 1 unit. 30 plus 1, 1. And if it is opposite to the external magnetic field, the 30 strength will be diminished by 1. Because it is 1, I am taking the example now. Here it will be minus 1, 30 minus 1, 29. In this case, 31 field strength it is observing, 31 units, and in this case it is experiencing only 29. That's why it will splits into 2 signal like this. This corresponds to the field strength of 29 and this corresponds to the field strength of 31. Like that, splitting takes place in NMR spectrum because of presence of adjacent nucleus, adjacent protons. In this case, we are having 2 different hydrogens. Here it will be oriented in 2 different directions. No, it will be parallel or opposite. Both will be parallel and both will be opposite to the field. If these 2 are in same direction, B naught having 30 and B naught is having 30, here 2, 32. Here no effective, no resultant, because one spin cancelled with other for these 2 hydrogens, and hence in this case here 30 only. And if you take this one, because of opposite direction, 1, 1, 2, 30 minus 2, 28. Like that, 3 different field strength will be observed by B naught, producing 3 signals in NMR spectrum. Like that, we will have different types of signals, that is, which is called as spin multiplicity, depending upon n plus 1 rule. Why n plus 1? Because if one proton is there adjacent to it, it is splitting as 2. If 2 are there, 2 plus 1, 3. Into 3 signals it is splitting. Like that, the intensities of the peaks will be defined by using Pascal triangle. See, I have shown the NMR spectrum of ethyl bromide. In ethyl bromide, we should get only 2 peaks, right? But because of spin-spin splitting, for this CH3 protons, because of two adjacent protons, 2 plus 1 is 3. This particular signal splits into 3. Like that, if you take this set of protons CH2, it is having 3 adjacent protons, 3 plus 1 is 4, like that it splits into 4, and hence the splitting is observed in ethyl bromide like this. And this is the same spin magnetic field strength. In this case, the CH3 proton is having 2 adjacent protons, and the orientation of spins of these nuclei will be like this, giving rise to a triplet in NMR spectrum. Whereas here we can have 4 signals. The combinations will be like this, and we will get 4 signals in NMR spectrum. And another phenomenon or another parameter in proton NMR spectroscopy is it is possible to measure the area of the peak. Here if you see the example of ethanol, 3 signals we got, right? The 3 signals are according to split according to the spin multiplicity, and the areas are, if you measure the areas of these 3 peaks, look at the slide, the OH is having the integration value of 1 and CH2 is having integration value of 2, and the methyl protons are appeared as a triplet in NMR spectrum with the integral value 3. Like that, the integral, from the integral values also we can produce further information for the determination of structure of the molecules. See, because of the wide applications of NMR, students, till now from 1944 to till date 5 Nobel Prizes we got. Let me tell you that one. In 1944, as I told you already, 1944 for Isoda Rabi for measuring NMR or resonance phenomenon in molecular beams. After that, in 1962, another Nobel Prize for NMR only for applying the NMR technique to solids and liquids. After that, in 1992, another Nobel Prize for development of NMR only for the development of 3D NMR. Sorry, HRMS, high resolution NMR technique. And after that, in 2002, another Nobel Prize for 3D NMR, 3-dimensional nuclear magnetic resonance. After that, in 2003, another Nobel Prize in medicine field for developing magnetic resonance imaging, which is popularly known as MRI scan. Like that, we have 5 Nobel Prizes for development of nuclear magnetic resonance spectroscopy, and I strongly refer you students to go for research in NMR after your post graduation, and I wish you all the best. And I want to wind up my lecture with a small exercise. Just please practice these one. Look at the slide. I want to wind up my lecture. The first question is, which of the following nuclei are NMR active? You all aware of that. And in the second question, I asked you to label the set of protons in these sets of molecules, and I asked you to draw rough sketch NMRs of these molecules, and you practice these questions at your home. Thank you one and all.